So what we are going to do today is to try to find a way to get good upper bound on the quenched free energy for the pinning model. Okay, so you know that with our notation here, we have this trivial bound for the free energy, or almost trivial bound that you get from Jensen inequality. Okay, because when you average the partition function with respect to the environment, the influence of beta disappears. And okay, so far we did some work to know how sharp this was, somehow to know how close these things were, by trying to get a lower bound on the free energy. But what we've not done is pushing things in the other direction, trying to find better upper bounds on the free energy to show that this is not sharp. Okay, so this is what we are going to do today. So the main objective, and also tomorrow, in fact, and the main objective of today will be to prove this statement. Okay, which is that when alpha is larger than 1, so in the case of not only recurrent renewal, but when you have a renewal with positive density, okay, because in that case the expectation of tau 1 is finite. So you always have a shift of the critical point, and the order of magnitude of this shift is beta square for beta small. Okay, so we only need to prove a lower bound because the upper bound is in fact trivial. Okay. Okay, an upper bound for UC beta is lambda beta, which is log of the expectation of exponential beta omega. And it's smaller than c times beta square in the whole interval 0, 1. Okay? Okay, so first we are going to start with a much more modest statement. So we will prove two statements. The first is that for all beta and u, for all beta positive, u positive, f beta u is strictly smaller than f0 u. Okay. And second, that okay. For all beta larger than 0, there exists c beta such that for all u in 0, 1, we have f beta u is smaller than u c beta u square. Okay, so okay, the first statement I don't have to tell you what this means. If you look at the second statement, it looked a bit like what I said, what I mentioned yesterday. So what we are going to prove tomorrow is that the free energy grows up at most quadratically. after the critical point. So this is not the same statement, because here, okay, the two things would be equivalent if the critical point was 0. But basically what this statement tells you is that either UC beta is larger than 0, okay, or star holds. Okay, meaning that in both cases somehow when alpha is larger than 1, when alpha is larger than 1/2, okay, these things are valid for all alpha. But when alpha is larger than 1/2, this is better than the anneal bound. Okay? So it tells you that either the transition is smoother than in the anneal case, or you have a critical point shift. Okay? But you're not sure in what case you are. Okay, so basically they are not the result we are looking for, but it's a good way also to introduce the tools we are going to use. Okay, so how do we do that? So one of the difficulty when you want to estimate the free energy is that okay, you want to take the expectation of a log, and it's not very something very convenient. I mean, you don't really know how to estimate that. So something which is quite common in statistical mechanics and which is called fractional moment techniques is to say, okay, in fact, we can bound that by an estimate which depends on a non-integer moment of Zn. Okay. So this thing, it's equal to 1 over theta, the expectation of log Zn to the theta. Okay. For any value, for any theta chosen in 0, 1. Of course, you don't need to choose theta in 0, 1, but this is the value for which the technique will have an interest. And then you use Jensen inequality, and you get that this is smaller than 1 over n expectation, log of the expectation of Zn to the theta. Okay, so as you will see, there are various reasons for which this is much better. This is much easier to estimate than this. So we'll see several of those. And basically, okay, what we want to show is that Zn is much smaller than its expectation. Okay. So, I mean, if Zn is much smaller than its expectation, this thing will be small. So, okay. So, okay, now let's take theta equal to 1/2. Okay, so the reason why you want to take theta smaller than 1 is that you want to get something better than what you got from Jensen inequality initially. You want to get something better than that. Okay, if you take theta larger than 1, you know that the bound you're going to have is worse than this just by using Jensen. And okay, let's try to estimate the expectation of square root of Zn. So, okay. If Zn is typically much smaller than its expectation, it means that the expectation of Zn is mostly, so you can underline the dependence in omega. It means that the expectation of Zn is supported by an event of very small probability. Okay? This thing, it is Z and U, as you know. Okay, on a very small event, this variable will be much larger than nu, and this is what makes the expectation. And on typical omega, this thing will be very small. So using this idea, what we can do is to say we want to introduce a function, gn of omega, which is small when Zn omega is large, okay, which is of order 1 when Zn omega is typical. Okay, it's somehow a function that penalizes the event that carries all the mass of this expectation. Okay, and we can rewrite this expectation in this manner. Sorry. It's not very mysterious. And then you can use the Cauchy-Schwarz inequality and say that this is smaller than the square root of the expectation of Zn gn omega times the square root of the expectation of gn omega to the -1. Okay, this is clear? Okay. So this is valid, in fact, for any positive function omega. But we have to find some function for which this inequality will be useful. Okay, so we can assume that the expectation of this function is 1. Okay, and in that case, this thing, you can see it as the expectation of Zn under a new probability measure. Okay, so you can define a new probability measure P tilde, whose density is defined by gn omega. Okay, and what you have is that the expectation of square root of Zn omega, it is smaller than the square root of the expectation of Zn under this new measure. And then you have this other term, which is gn omega to the -1. So the interpretation of this inequality here is that, okay, when you, so I mean here, if you take gn omega equal to 1, this is just Jensen. Okay. But what we do here is, okay, we do some kind of strange Jensen. we do Jensen, but we allow ourselves to change the measure. Okay, so by putting the square root out, you're allowed to change the measure, but you have to pay some cost, because this is larger than 1. Okay? And what we want to do is to do this for, okay, we want to somehow to make a change of measure that makes Zn smaller, and we don't want this guy to be too big. Okay, so this is we want to maximize the benefit of our change of measure and to minimize the cost. Okay, so we have to. So, okay, let's try the simplest thing. So, let's assume that, say, the omega are Gaussians. And you will see later that there is nothing very specific about Gaussians, but they are just simpler for computations. And what we will do is change the mean of our Gaussians. So at the beginning, you have centered Gaussians. And you want to choose a G which shifts the mean of your Gaussians. Okay? And somehow, well, if you lower the value of omega, you will lower the value of Zn. So I choose my omegas to be independent Gaussians of variance 1. Okay, as before. But I will choose to shift the variance of the omega n's. And of course, I mean, if I do it for every omega n, I will get a measure which is singular with respect to the original one. So that, in particular, I mean, you will have no density. In particular, this term will be infinite. But what you need to do is only to modify the environment up to the n step. You have no interest in modifying the omega after that. Because if you modify omega later, I mean, it will just bring you some additional cost here and won't give you any benefit here. Okay? Okay, so so can anyone tell me who Gn omega is in that case? Okay, so what's the density of E tilde with respect to the Lebesgue measure? Okay, so what you have is that okay, I consider that, I mean, there's a small abuse of notation, but I consider that this is a measure on, or n. Okay, I just consider the first n variables. You agree that this, the density, is 1 over square root of 2 pi to the n times exponential x squared minus x plus delta square over 2 dx. And you have a minus here. Omega, and here you have a product from n. Okay. Sum from n equal 1 to n omega n minus delta over 2 square d omega n. Okay. Okay, so now can you tell me the expression of the density of G and omega? Okay, exponential delta times okay, so you have some delta square times n. Okay. What else?
Symmetry of the
Okay. And what about the signs? Okay. Where do you have minus? Yeah. Okay, and then yeah, okay. You also have a minus here. Okay, I mean you want this to be equal to 1. Okay, and the Laplace transform. So you must have a minus here. Okay, so this is G and omega. Okay. So now what is the expectation of Zn beta u omega? In terms of, okay, a partition function of a pure system. Any guess? When you take the average of Zn over this new measure, what do you get? Okay, so you get the expectation of En times exponential sum from n equals 1 to n beta omega n minus lambda minus beta square over 2 plus u delta n. Okay. And what do you get by averaging afterwards? So okay, what you need to compute is just this quantity, okay, which is equal to this. So you get just exponential beta square over 2 minus delta beta. Okay, so what you get in the end is Zn U minus delta beta. Okay, you've shifted the environment by delta, so what you get is that the pinning parameter is affected by minus delta times beta. Okay, so this is the benefit you get from your change of measure. Now you can also compute the cost. Okay. So when you compute the expectation of Gn omega to the minus 1, you get exponential n times delta square over 2 times the expectation of this guy. Okay, and you get exponential delta square n. Okay, so what we've done, there are basically extremely trivial computation. Okay, so far. But the idea behind it is quite subtle. This idea of changing the law of the environment in order to change somehow to improve the estimate you have. So what you get is that the expectation so that 1 2 over n times log of expectation of square root of Zn omega, it is smaller than 1 over n log of Zn u minus beta delta plus delta square. Okay? So this is an upper bound for 1 over n, the expectation of log Zn, sorry. Okay, so when you pass to the limit, what you get is that f beta u, it is smaller than f0 beta minus delta u plus delta square. Okay, and so far you're completely free in your choice of delta. So you can apply this inequality for any delta. So let's see how this can give you these two statements. Okay. So for the first statement, we'll choose to take delta really small. Okay. So when you take delta really small, well, if you take the derivative, if you take delta equals 0, you have equality. Okay. If you take the derivative of this expression at delta equals 0, okay, you get d of minus d f 0h at minus this is very bad, u minus delta beta. Okay. If you take the derivative, you get this, okay, which is strictly less than 0. So if you take delta small, you get something that is strictly smaller than f0u. Okay. For delta equals 0, you get f0u. For delta in the neighborhood of 0, you get something strict. Okay? Okay, now the second thing, it's in fact easier. So let's take delta is equal to u over beta square. Okay, and what you get is that f beta u is smaller than f0, 0 plus u over beta plus u over beta square. Okay, so now this is for omega Gaussian. We'll keep the assumption that omega is Gaussian in the rest of the lecture because it will be more specific. But for this case, it's quite easy to show you that this is, well, this is not too special, and we can, in fact, do everything, use the same trick in the non-Gaussian case. And what you have to do when omega is non-Gaussian is to consider this change of measure. Okay? I mean, we had taken a density of this type, exponential minus delta times the sum of omega, and everything went fine. So let's take the same thing, and we just renormalize it so that it's still a probability density, and see what it gets. Okay, so now you don't shift the variable. You don't shift the mean of the variable. You change their law, but you do what is called an exponential tilt. Okay? Okay, so we have to do the same computation. What is okay. What is this guy? Yeah, I guess this is what. No. You just need to know what's the value of this guy. Well, it's not very complicated. It's equal to E of exponential beta omega n, okay, beta minus delta omega n, because you have a minus lambda of minus delta. Okay? So that's it, and you get exponential lambda beta minus delta minus lambda minus delta. Okay? So so what you get here is Zn of, and I will write it like this, lambda beta minus delta minus lambda of minus delta minus lambda of beta. Okay, because of this tilt, somehow this does not cancel with that. So you just have to keep all these terms. Okay? And I don't put them in exponent because it would be difficult to read. Now, if you look at the cost, exponential g, the expectation of gn of omega to the -1. Okay, so what you get is exponential n lambda minus delta, okay, which is already in the density. And then when you take the expectation of this term, okay, you have a plus sign because you've taken the inverse and you get lambda of delta. Okay? So what you get here is, okay. Well, you get some new u, which is written here, and you get this penalty, which is lambda minus delta plus lambda delta. Okay. So this inequality becomes f beta u smaller than f0 u plus lambda beta minus delta minus lambda of beta minus lambda of minus delta plus lambda of delta plus lambda of minus delta. Okay, so I won't go into the first point. It works exactly the same. So you can derive with respect to delta at 0, and you will get that the derivative here is negative. But let's look at the second point. So what we want is, okay, to find delta such that lambda beta minus delta minus lambda beta minus lambda minus delta is equal to u. Is equal to, no. Let's see. Minus u plus u is equal to 0. Okay, because, well, this is the best we can do. I mean, you don't want to, okay, you don't want to worry too much about estimating this stuff. So let's put the pinning parameter equal to 0. You don't need to push it. If you push it more, you won't win anything, and you will make this bigger. So. And let's try to see what's the value of this delta. Okay. So first, how do you justify the unicity of the solution of this equation and the existence? So if you look at this, okay. If you look at the derivative of this guy, so when you take the derivative, you get something which is negative. Okay, this is by convexity of lambda. Okay. So, okay, for delta equals 0, you're equal to u, the derivative is negative. So if u is small enough, this thing has a unique solution, okay? Because you have a function which is decreasing. Okay. Now, also what you know is that, okay, the derivative at 0 of this guy is equal to lambda prime of beta. Okay, because lambda prime of 0 is equal to 0. So for u small, you have delta beta u, which is equivalent to u over lambda prime of beta. Okay? This thing, this is equivalent to lambda prime of beta times delta for delta small. Okay, just taking minus. Okay, just using the Taylor formula. Okay, now you know that lambda of delta plus lambda of minus delta, it's equivalent to delta square. So you can just compose the equivalent, and you get that f beta of u, well, it's smaller than, okay, 2 u square over lambda prime of beta square for u, well, smaller than, okay, for u which is in the neighborhood of 0, which is not explicit, which depends on beta. Okay, because you've taken two equivalents. Here I put the constant 2 to be sure that I'm above my equivalent, and basically I get the same square bound. Okay, so for beta is small, this is roughly let's see. Yeah, when beta is small, this is roughly beta. But for beta large, the constant gets different. Okay? Okay, and here I've written for all u in 0, 1. So if this is true in a neighborhood, basically by changing the constant, you can make it true in 0, 1. This is not really important. Okay? Okay. So these are nice results, but okay, if you try to do things this way, you can never get a good bound on the critical point. And the reason is that, okay, if you want to truly modify the partition function, what's the expectation of the partition function on the exponential scale, you have to pay some exponential cost here. And therefore, this term will be positive in the end. So when you pass through the limit, I mean, the bound you will have, you get here, has to be something positive. It can't be 0. Okay, just because the cost of the change of measure is exponential. Okay, but if you remember, when we were aiming for lower bounds on the free energy, or lower bound on the critical point, what we said is, okay, we have some n, which is such that this guy is positive, and we're done. Okay, so what we would like to do now is to try to, okay, still use this powerful machinery and kind of simple machinery, but to combine it with some kind of what I would call a finite volume criterion. Basically, you want to have some condition which is, if it's valid for a given n, then you're done and you can say that the free energy is equal to 0. Okay? So, okay, let's try to do that. Okay, any question on this part? Okay, so from now on, I will call AN the fractional moment of Zn. Okay, and theta will be something between 0 and 1. And what I want to have is something like a kind of recursion, a recursive relation on this on this AN, so that okay, if I know that until some rank the AN are sufficiently small, the recursion will somehow tell me that they are all small. Okay, so what can I do to estimate? Well, if I okay, let's try to have a recursive relation on Zn already. So Zn beta u omega. You can say that okay, it's equal to the sum from n equal 1 to n minus 1 of Zn beta u omega. Okay. So this n, it will just represent the last point that you, okay, n from 0. Okay, and this n is just the last renewal point before, strictly before n. Okay. And then you have to multiply it by kn minus n, exponential minus exponential beta omega n minus lambda, okay, minus beta square over 2 plus u. Okay? And from now on, omega is Gaussian. Okay, so if I want to transform it into a recursion on AN, basically, I will lose the equality and get an inequality. So I have theta, which is smaller than 1. So I use the fact that, okay, if I take a sum of numbers to the theta, or sum of positive number to the theta, it's smaller than the, well, okay, basically you can take the theta into the sum, it will get you an inequality. Okay, you just have to check this for two numbers, and then you can iterate and check it for two numbers, just simple analysis. Okay, you do this, you average, and you get that AN is smaller than the sum from n equal 1 to n minus 1. Okay, k n minus n to the theta. AN. And then what will come is exponential beta square, okay. theta u minus theta 1 minus theta over 2 beta square. Okay, I mean here the theta multiplies what you have in the exponential here, so when you take the average, you kind of see it. So it's the lambda beta for the Gaussian. Okay? Yeah, we are in the Gaussian case, and as I told you before, it's not a big difference. Okay? But it makes computation simpler. I think notations are already complicated enough. We can take some simplification. Okay, so now what can we say from this recursion? Okay, so get a lemma, which tells you that, okay, if rho is such that the sum from n equal 1 to n n equals 0 here, n equal 1 to infinity of kn to the theta times exponential theta u minus theta 1 minus theta over 2 beta square. If this guy is smaller or equal to 1, no, if okay. Theta, beta, and u are such that then f beta u equals 0. Okay? So why is that so? Well, just look at an. So okay. An, it's smaller than the max of a0 a n minus 1. Okay, I suppose that n is larger than 1 times the sum from n equals 0 to n minus 1 k n minus n to the theta times exponential my thing. Okay, what I just do is I replace this guy by the max over all indices. And what I get is that an is smaller than rho of the max of all the guys. Okay, so then by an immediate induction, in fact, I can say that for all n, an is smaller than a0. Okay, and which is equal to 1. Okay, and this gives me for free that the free energy is equal to 0. Okay, so now what does this give me? So it can be useful, in fact, only if theta is taken larger than 1 over 1 plus alpha. Okay, because if theta is smaller than this sum will be infinity. you will have an exponent here which is larger than -1. So, okay. So let's call eta the sum from n equal 1 to infinity of kn to the theta. And my criterion is just I want, let's see. Okay. If beta is larger than square root of log eta plus theta u over, okay, times 2 over theta times 1 minus theta. Okay, so just trust me, this is then f beta u is equal to 0. Okay, so in particular, if beta is strictly larger than square root of 2 log eta over theta 1 minus theta, then this is satisfied for some positive u, and uc beta is larger than 0. Okay, so what this tells you is that okay, for any alpha, if your environment is Gaussian, if you take beta sufficiently large, you have a shift of the critical point. Okay, so then you can say, okay, but here we have some kind of freedom somehow. I mean, if you take theta very close to 1, somehow, well, this eta here should be very close to 1. Okay? I mean, when you take theta equal 1, this is equal to, so the sum is equal to 1. So if you take theta close to 1, this is close to 1. So maybe beta would get small. I mean, maybe this thing would get small there. But the problem is that you divide also by theta. So basically, you can't hope to get much better than this. Like, you can optimize over theta, but it's not very spectacular. Okay, but still, like, with a very simple computation, what you get is that, okay, you have a shift of the critical point. And at the time when this was discovered, somehow the question was open for 10 years. So. Okay, but it does not tell you anything for, you have no hope of this method giving you anything for small beta. Okay, and okay, I told you that making things Gaussian do not change much. Well, it's not really true. Like, as we've seen last week, okay, when alpha is smaller than 1/2, somehow there are some distribution for which the variance stays bounded for all beta. Okay, so basically, if you replace beta square over 2 by lambda of beta, and you plug this in, somehow this condition might be never satisfied for any beta. But there is no special trick. There is no contradiction anywhere. Okay, so now let's try to change a bit this decomposition in order to have a criterion that, well, does not only use the kn, but also use some of the n. Okay? So I will try to draw something. So here is how we should decompose the trajectories. So to be sure. Okay, so I fix an integer k, and what I want to do is decompose trajectories according to the last point of contact before. Okay, so it's not k, it's n minus k. The last point of contact before n minus k, and the first point of contact afterwards. Okay. Okay, so I will call one of the points n, the other point m. Okay, and I assume that it's kind of arbitrary, but that m can be equal to k and n cannot. Okay, just for the sake to have an equality in the sum. Okay, and to be sure not to count things twice. So what I get is that Zn omega, it is smaller than the sum from n equals 0 to n minus k minus 1 of Zn omega k m minus n exponential beta. Okay, sorry. This is what I wanted to write. Beta. Okay, this is n minus m minus n exponential theta exponential omega n minus m times beta, and okay, minus beta square over 2 plus u, and then you have to put back z m theta n minus m omega. So here it's the shift operator, okay, it's not the theta. Okay, and here I have to sum also over m from 0 to k. Okay? Okay, so now I take the corresponding fractional moment. So I get that an is smaller than the sum from n equals 0 to n minus k, the sum from m equal 0 to k. And what I get is an k theta n minus m minus n. Okay, and I get the same term, exponential minus beta square theta 1 minus theta over 2 plus u. Okay, and let's try to see how this can improve our our finite volume criterion. Okay, so what we get is that if okay, so now we get a row that is slightly more complicated, okay, but which uses somehow the value of an up to step k. Okay, and basically, well, there is a great advantage here is that when you want to estimate these guys, well, you can use the change of measure method that we've used to show that these guys, they will be small up to some step, okay? And then you will try to use that for the best k, and you will hope that this will be sufficient to make rho smaller than 1. So this is more or less the idea. Okay, so the reason why this is true is the following. Okay, so there is something missing in the formula here. You have an, but you have also am. Okay, that comes from this guy. Okay, so now let's take n larger than, say, k plus 1. Okay, so you know that an, okay, what we will do is this guy, we will replace it by its maximal value. Okay, so, and you have the exponential thing as well. Okay, so let's not care too much about this exponential term because it's the same in the two things. And let's just show that this double sum is smaller than what we have in the row. Okay, so in order to show that, what you have to do is, okay, to make some change of variable, because you don't want this n minus m to appear here. So let's see. Instead of taking this is equal, okay, so you take the sum with respect to m first. And then here you will make a change of variable. So you know that this index when n is equal to 0, it's equal to n minus n. Okay. And when n is equal to the maximal value, it's equal to k minus m plus 1. So this is what you get. Okay, and this is smaller than what you get if you sum up to infinity. Okay, so now we have this criterion, and we will try to show that okay, it's valid for some positive u for any value of beta when alpha is larger than 1. Okay, is it clear? So, okay. Let's take alpha larger than 1. And I know that, okay. If I look at Kn, not only it's summable in this case, but I also have a sum of nkn, which is finite. Okay. So we just choose the theta such that this remains true if I take the power theta here. So what I want is theta times 1 plus alpha larger than 2. Okay, so for the sake of definiteness, you can take theta equal to I guess 1 over 3 plus alpha is okay. 4 over 3 plus alpha. I guess this is fine. Okay, it's smaller than 1. Okay. So so what I have in that case is that the sum from m equals 0 to infinity times the sum from n equal m plus 1 to infinity of k theta n, it's equal to eta, which is finite. Okay, I mean this thing is just this thing. Okay, so basically if I replace an here by a constant, I get something which is finite. Okay, so then if I can show that all ans are small, or all important n are small, then I'll be fine. This is more or less the idea. Okay, so now we'll choose k large enough such that sum from m equal k over 2 to infinity times the sum from n equal m plus 1 to infinity of k theta n is smaller than 1/2. 1 over 2e. So, okay, I mean, this is arbitrary. I mean, if k is large, okay, I mean, this tends to 0 when k is, tends to infinity, okay, just because the sum is finite. And, okay, I just want to take k large so that large values of k here, they don't count that much for the whole sum. And the reason why I want to consider this thing is that, okay, large values of k here. Mm-hmm. Yeah, okay, because large values of k here, in fact, they correspond, large values of m here, they correspond to small values of m. Here, well, okay, we'll see just now why I want to have these conditions, well, why I made these definitions. So, lemma. So, okay, suppose that u is smaller than 1 minus theta beta square over 2. Okay, I mean, I'm interested in u that are of order beta square, so this is not a big restriction, and this allows myself not to care too much about the exponential factor. Okay, so let's assume that this is true, and if for all m smaller than k over 2, am is smaller than e, and for all m in k over 2, k am is larger than 1 over 2, is smaller than 1 over 2 eta, then rho is smaller than 1. Okay? So basically, to control rho, you don't need to control the a that are the a for small k's, but you need to show that the a for big k's are small. Okay, and the reason is quite elementary. It's just you use the definition. If you look at, okay, the sum from m equals 0 to k over 2 of am times the sum from n equal to k minus m plus 1 to infinity of k theta n. Okay. By 1, by assumption 1, it is smaller than okay, e times okay, but here you want to make the change on a variable. K gives n minus k, and what you obtain is this sum here, or this sum here, but which ends up somewhere here. Okay. So this is smaller than 1/2. Okay. What about the second term? So if you took the sum from m equal k over 2 to k of am times sum from n equal k minus m plus 1 to infinity kn of theta, well, it is smaller than 1 over 2 eta times the sum from m equal k over 2 to k times the sum from n equal k minus m plus 1 to infinity of kn. Okay, and this is smaller than eta because, well, this is a subsum of the big sum. Okay, so what you get is smaller than 1/2. Okay, so what we need to show really is that, okay, when m is of order k, am is small, and to have a reasonable control for the other m. Okay. And well, remember that we can choose. In fact, I mean, here we can basically choose everything. Okay. Okay. Theta and beta, they are fixed because, but we can choose the value of u and we can choose the value of k. Okay, so what we choose is to choose u is equal to, well, k is equal to u minus 1. Okay, and the reason for that is that if you make this choice, what you have is that am, okay, it's the exponential expectation of z m beta u omega to the theta. Okay, it is smaller than the expectation of Zm beta u omega. Okay, let's use the stupid bound first. And you can see that this is smaller than exponential times u. Okay, this is just ZUM. Okay. And ZUM, it's smaller than exponential mu. So this is smaller than exponential mu theta. Okay, you know that m is smaller than k, so this is smaller than e. Okay, so choosing k equals to u minus 1 is just saying, okay, we want to be sure that the expectation of the partition function has not exploded yet. Okay? Because as we want to show that the partition function is small, it's better that we know already that the expectation is not too big. Okay, and the reason why we are not losing too much here is that, okay, alpha is larger than 1. So that you typically have of order n contact at the critical point. I mean, when you're, okay, this bound here is not too bad. Okay, because basically the probability of the last point being a contact point, it's of order 1. Okay, and you have a positive density of contact when u is positive. So, okay, so I mean, if you had alpha smaller than 1, you would have to do some thinking before choosing. Okay, now for m larger than k over 2, we have that, okay, exponential, the expectation of Zn omega to the power theta, it's equal to this. Okay. And now I can use Hölder inequality, and I will get that it is smaller than, okay, the expected value of Zn to the power theta times the expected value of Gn omega to the minus 1. Sorry. To the minus theta over 1 minus theta to the 1 minus theta. Okay, so this is just Hölder inequality. Use Hölder inequality with P equal 1 over theta, 1 minus theta, 1 over theta, and Q equal 1 over 1 minus theta. Okay? This is An. So now, I mean, we want to show that An is small, so we won't allow this term to be exponentially big. So what we want to choose is a change of measure that does not change too much, in fact. We want a typical event under this measure to be a typical measure event under the original measure, in a sense. Okay? So, so I will do the same thing as before. I will change omega to omega minus delta. Now my question is, how big can I take delta, or how small should I take delta for the two measures to be not too different? Any guess? Okay, so what's the typical value of this guy under the original measure? Or the typical order of magnitude of this guy? No, I mean, what's the under P? What's the typical order of magnitude of this guy? Sorry? The variables, they are centered. They are centered Gaussians. So this is just a Gaussian of variance n. Okay. So it's typically of order square root of n. Okay. Okay, so I want to change the mean in a way that, this sum won't change too much. So what I want is that I want this shift of the mean of this big guy to be not larger than square root of n. Okay, if I make the shift bigger, you will be able to tell the difference. If I make the shift smaller, basically you won't be able to tell the difference from the two measures. Okay, because this is really the quantity that... Okay, so for this reason, I will choose delta to be equal to 1 over, either 1 over square root of k or 1 over square root of m. It does not make much difference. Okay, and I will choose gm, let's say 1 over square root of m. Gm omega is equal to exponential sum of n equal 1 to m of omega n over square root of m. minus 1/2. Okay, the 1/2 is just m times delta square over 2. Okay, and you see that indeed the measure is close to the original one because okay, the density, it's the exponential of a normal of variance 1. Okay, and what you have is that is the exponential of g n omega okay, so you have theta over 1 minus theta times 1 minus theta. Well, it's exponential theta over 1 minus theta. You have a 2 here. And I guess that's it. Okay. Let's see. Yes. Okay. I think that's it. So it's something finite. So what we have to show now is that this guy is smaller than epsilon, for epsilon arbitrary. Okay? Because you need to beat this factor and you need to beat also this factor. Okay. So So we want to show that, okay, the expected value of Zn u somehow is small, but just let us think for a moment of what would happen for if u were equal to 0, okay? If we can show that this is small for u equal to 0, if you enlarge a bit the value of u, normally it should be okay. And here, I mean, I just want to show why this kind of technique works for, in general, for alpha larger than 1/2, okay, but does not work for alpha smaller than 1/2, okay? So this guy, it's equal to Z n minus beta delta n, okay? So it's equal to Zn delta over square root of n, beta over square root of n. Okay, when you average, you just see the influence of the shift. Okay, so from 0, you go to a tilting value that is, okay, negative, but in a way that decreases to 0 when the size of the system gets large. So the question is, to what condition did my change of measure really change the value of Z, okay? I want to get something that is really much smaller than the expectation. If I don't get that, basically, all I've done is lost. I mean, it was much easier to do Jensen from the beginning. So I want to be sure that by not doing Jensen and making my change of measure, I've won something, and this is just saying that I've won something. Okay? So let's look at the partition function without constraint, because it's slightly easier to see. So let's look at the expectation of exponential minus n equal 1 to n delta n beta over square root of n. Okay? And we want to show that this is much smaller than 1. Okay, for n large. Because when the pinning parameter is 0, of course, this is equal to 1. So the question is, what is the typical behavior of this guy? Well, this guy is not too, so this is Hn of tau. Okay, and Hn of tau is not something too nasty. Like most variables, it behaves like its expectation. Okay, and we know that the expected value of Hn of tau, it is equal to n to the alpha. Okay, so okay, this guy, it is larger than the expectation of minus beta over square root of n times Hn of tau. Okay, this is just Jensen. And therefore, if alpha is smaller than 1/2, the benefit you get of this change of measure is really rubbish. Like when n gets large, your benefit is getting smaller and smaller. Okay. On the contrary, when alpha is larger than 1/2, okay, well, this is a lower bound, so this is not very indicative, but more or less, at the beginning, when this starts to diverge, this is almost an equality. Okay, after this it starts to be different, but okay, when alpha is larger than 1/2, basically, the change of measure you can make a gain out of the change of measure, and then you have some kind of complicated machinery that you have to plug into that in order to be sure that you get a benefit. So let us see in detail how this works for alpha larger than 1. Okay, so when alpha is larger than 1, I mean, we have a benefit that grows up like square root of n, so it should not be too much of a problem. Okay. So M of Zm omega, it is equal to Zm u minus beta over square root of n. Okay? So we want to be sure that we've chosen u such that this is negative. Okay? You want, say, this factor to be at least twice as large as this one. Okay, so I guess we can make things that. So u minus beta over square root of m, you want it to be larger than, say, minus beta over square root of k. Minus beta over 2 square root of k. Okay, so let's see. So this is what we want. This is k minus 1. And you have beta square. Let's take beta square equal a small constant times u square. Okay. And u square, it's just k to the minus 2. U is equal to a small constant times beta square. This is what I meant. Okay. And we want to show that if we choose C small enough, the free energy is equal to 0. Okay, so what we have here is c to the minus 1/2 over square root of k square root of m. Okay. So this is smaller than this, okay. So this is equal to this. And this is smaller than, okay, c minus 1/2 over 2k, provided that you've chosen c small enough. Okay? So now what we want to show is that okay, and this is smaller than c minus 1/2 over 4m, by the way. Okay, now we want to show that Zm times, okay, for this, sorry, minus c minus 1/2 to the 4m. Wait. If you take a large constant b, okay, so lemma, for m large enough, for all epsilons, there exists b such that for all m larger than m0, this is smaller than epsilon. Okay, if we can show that, then we say, okay, we choose c sufficiently small, and then we are done, because we have estimated all the partition function for the modified guys, and you take it to the power theta, it doesn't change much, and you can plug it into the lemma. So why is this small? So, okay. If you look at this guy, okay, you can always say it is smaller than the probability that Hn of tau is smaller than gamma n plus exponential minus gamma n times h. Okay, so here you have just exponential minus hn tau, and you also have some boundary condition, but let's drop it. We want an upper bound. So either hn tau is small, and you know that the contribution is smaller than 1, so the contribution you get is the probability of this event, or hn tau is large, and in that case, well, you know the exponential is smaller than this. Okay, so this thing is smaller than exponential minus gamma b, so if you choose b large enough, it will be smaller than epsilon over 2. Okay? Well, I still need to tell you who gamma is, but this is coming in a moment. So now we want to choose gamma such that this is small. Okay? But recall that the expectation of tau 1 is finite. Okay? So by the law of large number, the limit when n tends to infinity of e hn of tau over n, it's equal to 1 over the expectation of tau 1. Okay? I mean, you just Yeah, it's basically the law of large number, like, just a bit more than that. But because okay, n it's somewhere in between hn tau hn of tau and tau hn of tau plus 1, okay, by definition. You know that this guy, it is equivalent to hn of tau times the expectation of tau 1. Okay, and the same for this guy, so you get this limit without the expectation. Okay, no, so, and this is what I want. Okay, this is true in probability. I mean, this is also true almost surely, but this is not. Okay, so in particular, if we take gamma equal 1 over 2 exponential of tau 1, this guy goes to 0. So it's, in particular, it's smaller than epsilon over 2, if n is sufficiently large. Okay, so if alpha were smaller than 1, what you would take here is n to the alpha. And you would have to choose somehow some kind of different power of m here. But basically, okay, things are easier in the case alpha larger than 1, okay? But it's only on the technical level. Like qualitatively, basically all the ingredients were there. Okay, so I have 10 minutes left. So, well, this encloses the proof of the fact that you have a critical point shift at every temperature when alpha is larger than 1. You've seen from heuristical reasons that okay, it will also be the case for alpha larger than 1, larger than 1/2. Okay, now the question is what happens for alpha equal to 1/2? Because you know that for alpha equal to 1/2, we've not been able to prove that you have no critical point shift. Okay, because I mean the second moment it blew up much more slowly than in the other cases, but it still blew up. So we couldn't use the second moment method to say that. But if you look at this method, and I mean just the very basic idea, like without even caring about the technical trouble you might have later. When you do the change of measure, what you get in the case of the simple random walk is here you will get exponential minus beta, because this guy it's over the square root of n. Okay, so you will get something that is, I mean, if beta is small, you will get something that is not good. I mean, the reason why the technique works is that when n gets larger, the estimate you get improves. But this is not the case when alpha is equal to 1/2. So, okay, maybe the problem is that the change of measure we make is not the right one. So we decided to change the means of the Gaussian. But what could you, do you have any suggestion, like other kind of change of measure that would allow you to do? Okay, so, well, so what turned out to be the right idea, and it's a bit difficult to explain why, but for alpha equal to 1/2, what you have to do is somehow not change the mean of the Gaussians, because it does not give you something sufficient, but you have to change the covariance, okay? So what you will do is, instead of taking the omega independent, you will take them negatively correlated. Okay, and when you take them negatively correlated, when you take the expectation of this sum, okay, you will get something which which is smaller due to the fact that there are negative interaction between the terms. So, okay, I guess to give a clear intuition for the picture why this is better than simply shifting the mean, it would take a long time, but basically this is just to tell you that okay, this case is a bit mysterious, but somehow you can get through using some of these ingredients with some kind of new ideas. Okay, so I will stop here, and tomorrow we will see the smoothing of the free energy curve. And if he can reassure you, I guess it's a bit less technical than this. So it's not easy stuff, but it will be more